In this video, we're going to look at some code that works with an array list, and we're going to consider both the theoretical and also the empirical or measured big O of three different methods. So we're going to look at a method that runs in constant time, a method that runs in linear time, and a method that runs in quadratic time. And we're going to look at the code itself to try to determine the big O theoretically, just from looking at what's going on in the code. And then we're also going to run it with some test values and just get a sense of empirically, or kind of from a testing perspective, from an experimental perspective, what the running time actually looks like in actually running the code. So what we're going to do here is we're just going to start by filling up an array list. And note that it's very important we're using an array list. So this would be similar to using an array. I'm not using a general list because list has lots of different implementations, and how an array list will work actually would be very different from how a linked list will work. So I'm using specifically an array list. You could also do these same examples with just an actual, int array, but we're going to try it out with an array list. So what I'm going to do is I'm just going to fill that list up with some random numbers, and then I'm going to accomplish three different tasks. I'm going to have a method that just gets the middle value. So just goes to however big your array is, goes to the middle index, gets that value. I'm going to have a method that calculates the sum. So just totals up all the numbers on the list. And then I'm going to have a method that figures out if there's any duplicates on the list. So those are going to be our three methods. We're going to write the code, evaluate the code by looking at it and looking at the structure and the loops and the methods, and then we'll also run it and take a look at the actual time. So the first thing we're going to do when we have our declare and initialize our list is we're just going to fill it up with random numbers. So I have a method here to do that. I just specify how many numbers I want in my list, and then I am having my range be basically twice that size, and then I'll just fill up the list with random numbers in that range. I left these numbers all in here as variables, so if you want to play around with that size and when you're kind of modifying this code and playing with it, you can kind of change that, and the random number generator will still work. So that method's going to fill up my list. When we're dealing with our smaller lists and testing out our code, we'll print out the list to just see what the value is. And then I have some timing code in here. So some of this code uses classes from the java.time package, which was introduced in Java 8. And the purpose of this is just to time how long certain code takes to run. So we're not really covering these. You're not expected to know how this part works, but just know that this is the current way that you can time a section of code. So you essentially just figure out the instant when your code begins. So I collect an instant moment right there. I then run my code. So I'm invoking that get middle value method. And then I get the instant when it's done. So these two instant objects are basically just figuring out when did the code start and when did the code end. I then figure out the difference between them, and I'm going to print it out in milliseconds. So all of this timing code that's around here is just figuring out how many milliseconds did this code take to run. So that's all it does. So let's start out, and we'll start by writing our first method. So our first method is get the middle value. So we're going to send in an array list. Again, note that we are using an array list, and we just want to return that middle value. Well, how do we find the middle value? Well, how many numbers are in our list? That's going to be number list.size. The middle value, the middle index, is going to be that size divided by 2. Okay. Now I'm not going to really worry right now about, even and odd lengths and get too specific about which number we want to use, because that's beyond the point of what we're trying to do here. Right now, I just want to demonstrate a couple of different methods with different efficiencies. Okay, so we'll get that middle index, and then we're just going to return our number list, getting that value at the middle index. Now, we have talked about the idea that there's basically two things that in general affect our efficiency of a method. One is loops. This method doesn't have any loops. And the other thing that can affect the efficiency of a method is method calls. So a lot of times we'll invoke a method on some object or invoke some other method that we've written, and we might not know the efficiency of that method, but it might affect the efficiency of our method, right? Because what the efficiency of this get method is going to affect the efficiency of our get middle value method. Now, looking up the size is constant time, but what about the get method? Well, let's remind ourselves that in the array list class, if we scroll down to the get method, Actually, it's not written in the get method. We can scroll up to the top. A lot of times the efficiency information will be in the description of the class. So we can look at the get method in the get section, or we can look here and we see that size is empty, get, set, iterator, and list iterator all run in constant time. Okay, so the get method is constant time per the ArrayList API description, and the size method is too. So here we have two constant time method invocations, which means this whole method is going to be running in constant time. Which is O of 1. And what that means is this code, this method, is not dependent on the size of the list. So if you send in a list of size 10, it's going to take 1 unit of time to get the size and 1 unit of time to get the value at that position, at the middle index position. That's going to be the same amount of time it takes if you send in a list of size 100 or 1,000 or 10,000 or 100,000 or a million. The execution time of this method is not going to change based on the size of the list changing. So you can double the size of the list, quadruple it, multiply it by 10. That's not going to affect the running time. Okay. Remember again that it doesn't mean that the running time is 1, right? The running time might be 100 units of time or 1,000 units of time. It just means that that running time, that how long it takes the method to execute, it doesn't depend on the size of the list. It's not going to change based on the size of the list. Okay. So let's actually just run this and make sure, first of all, that our code is working. We've only written the one method so far, but here is our list of 10 values. The middle value is 5. Okay, so 10 values in there, and value is 5. I'd say 1, 2, 3. Right, so because this is array lists are 0 based, the value at index 5 is actually 1 past the middle. But again, I'm not really concerned about that. We're not writing code to actually worry about finding the quote middle value. I just want to find some specific value. And the point is that for the method that we wrote for an array list, that code is going to run in constant time, right? So basically I can increase the size of my list to 100. It still ran in 0 milliseconds. Let's comment out the printing of the list for a moment. I can increase the list to size 1,000. It ran in 1 millisecond. The difference between 1 and 0 milliseconds is, negligible for what we're talking about. 10,000, 2 milliseconds, 100,000, 1 millisecond, and so on. So here I'm, multiplying the size of my list by orders of 10, and my running time isn't changing, right? It's not growing along with as the size of my list grows. So that's a constant time algorithm. Okay, let's now look at our next method, which is calculate sum. So again, we're going to pass in the array list, and we just want to calculate the sum of all of the numbers on our list. So we can start by declaring our sum variable. And then we're just going to cycle through the list. Now we could use a traditional for loop, or we could use an enhanced for loop. Because I want us to actually look at the method calls, I'm going to use a traditional for loop, but note that it is recommended that when dealing with the collection classes like list, array list, and particularly linked list, it is recommended that you use the enhanced for each loop. So for general code practices, you should use the enhanced for each loop. But for this particular example, I want us again to really look at those method calls, and some of the for each stuff happens behind the scenes. So I'm going to use a traditional for loop. I'm just going to say for int I equals 0, I is less than number list.size, I plus plus, and I'm just going to say the sum is going to be incremented by number list dot get the element at position I, and then I'll just return that sum. Now, when we look theoretically at this code, we can see, these are constant time statements. They're not dependent on the size of the list, but here we have a loop. With loops, we always need to look carefully at what's going on in the loop. So the first thing to look at is how many times is the actual loop running? Is the loop itself, the for loop or while loop or whatever it is the loop itself dependent on the size of the list? And in this case, it is, right? Because the loop is going to run as many times as the size of the list is, right? If we have a list of size 10, this loop is going to run 10 times. If we have a list of size 1,000, this loop is going to run 1,000 times, right? So here our loop is dependent on the size of the list. So that means that as our list grows, the number of times this loop executes is going to also grow. And it's going to grow at the same rate, right? Again, if our number list is size 10, the loop is going to execute 10 times. If we double our list to be size 20, the loop's now going to run 20 times. If we double our list to be 40, the loop's now going to run 40 times. So the loop is dependent on the size of the list, and it's dependent in a linear way, meaning if we double the size of the data set, we double the number of times the loop runs. If we take the data set and multiply it by 10, the number of times the loop is going to run will multiply by 10. Okay, so they are dependent, the loop is dependent on the size of the list and in that linear way. So the one thing we always want to be careful about is those loops. The other thing we need to be careful about again is method calls, and in particular method calls that happen inside of a loop. Okay, so here we're invoking the get method. Now we already looked up before and reminded ourselves that the get method is constant. It's O of 1. So this isn't going to affect the overall efficiency of our method, our algorithm, because this, how many times this happens, is not dependent on how many the size of the list, right? It's going to execute based on how many times the loop executes, right? But it's not going to change based on how big the size of the list is, okay? So that means that this whole algorithm, this whole method is linear time, O of n. And again, that means that the method is dependent on the size of the list. As the list increases, the time to execute also increases, and it increases at the same rate. So, for example, if we double the size of the list, we double the time it takes to execute. And again, approximately, right? We're not going to look at exact doubling here, but the idea is they're increasing at the same rate. So this is the key phrase here, is at the same rate. For linear code, your increase in your running time is linear. It's in the same rate as the increase in your data set, the size of your data set. Okay. So if we go up and run this, so again, we're going to start out with just a list of size 10. And here I have that same timing code where we'll just time how long that calculate sum takes to run. And we have a list of size 10. So there's our middle value. Here's our sum. Again, 0 milliseconds. This is pretty fast, for a 10 element array. Let's increase to 100. Now it's still 0 because that's, again, still pretty fast. Let's comment out the printing as we continue to make this bigger. So let's try a list of a size 1,000. Still 0 milliseconds. Let's try 10,000. Okay, so now it took 2 milliseconds, 1 millisecond, 2 milliseconds. Okay, it's still pretty fast, 22 milliseconds, 2. So it's still pretty fast, but we might be able to see some changes now. So let's now kind of increase our list size. Let's start doubling it. And also keep an eye on the fact that this middle value timing should remain the same, approximately the same, right? Because it's constant time. So for our list size of 10,000, let's say it's going to take about 2 milliseconds. So let's double that to 20,000. Now it took about 6 milliseconds. We do it again, it took 4, right? So again, it's not exact, but it's approximately doubling, right? 3, 4, 6, that's about double from 2, okay? So let's now say it's about 5. Let's double it again. Let's make our list size 40,000. So we're doubling the size of our list. And now let's say it was around, 4 or 5. Well, now it's around 9, 8. Again, it's doubled again. So we've doubled the size of our list, and we've doubled the amount of time it took to execute our method. Because again, the list and the method size are increasing at the same rate. Notice again that this constant time algorithm hasn't changed. Okay, let's double it one more time to 80,000. Again, we were at here, 7, 8, 9 milliseconds for the 40,000. If we double it, we're up around, 19, 21, 15, again, approximately double. So this gives you an idea of, again, we're doubling the size of the data set, and in doing so, we, approximately double the amount of time it takes to run that method. So our data set and our running time are increasing at the same rate, and that's what it means for linear, okay? Let's write our final algorithm, which is going to be quadratic time. So this is going to be the method that looks for duplicates. So what we're going to do here, there are definitely efficiencies we could make to improve the method I'm about to write. But again, the goal of this is not to write the best contains duplicate method that we can write. It's instead to just demonstrate some code that runs in n squared or quadratic time. Okay, so yes, I'm fully aware that there are better ways to determine and more efficient ways to determine a duplicate, but I'm going to use kind of the brute force way just again so we can see what's going on with this code. Okay, so to do that, I'm basically just going to use a nested loop. All right, so I'm going to start off by saying, okay, do I have any duplicates? Well, let's assume that I don't. And then I'm going to have a loop that goes through my list. And I'm again going to use a traditional for loop just because I want us to really be able to evaluate the method calls. Then I'll get the current number that I'm looking at. So this is the current number I'm looking at, and I want to see if there's any duplicates in the list. So what to do that, I'm going to look through all the other numbers in the list. So I'm going to say, okay, let's look through everything else in the list. J equals 0. J is less than number list.size. And I'm going to say, well, if my, well, let's call it a compare number. So if my current number is equal to my compare number, and of course, if I is not equal to j, so I'm not looking at the number in the same position, right? Because obviously the number in position I and j, if they're equal, is always going to be the same because it's the same number. So if we're not looking at the same position, but we're looking at what we have the same number, then we found a duplicate. And then at the end, we'll just return that result. Now, there are a couple of very easy things I could do to improve this method. First, I could stop any of these loops as soon as I find a duplicate, right? Because as soon as you find a duplicate, all I'm doing with this method is returning a true or false, right? So once I find one duplicate, I don't have to keep looking for others. I can bust out of these loops, just return true, right? The other thing I could do is I could start my inner loop at I+1, right? I don't technically need to look back at all the numbers I've already examined. Okay, so obviously things I can do to improve the efficiency of this method. Note that I'd really only be improving the actual run time, the amount of time it's going to take, the real world time. Even with all those efficiencies I just mentioned, the code's still going to be O of n squared. So in real world terms, it will run faster, but it's not going to improve the big O. The big O is still going to be the same for all those improvements I just mentioned. But again, I'm not going to make those improvements because I really want to just focus on what a nested loop looks like in terms of a quadratic method. Okay, I do encourage you to make some of those adjustments, some of those improvements, and really look at how that affects the real world timing. Because again, we always need to kind of think about two things. We have to think about this theoretical big O, right? What is the big O of my code? Is it O of 1? Is it O of n? Is it log n? Is it n squared? That's really important. You want to make your code as efficient as you can. But not all O of n code is created equal. Not all quadratic code is created equal, right? In the real world, if you have, quadratic code that is more efficient than other quadratic code, which is less efficient, that matters, right? Real running time does matter. So you kind of have to keep these two things in mind. You have to keep it matters first, the theoretical running time, the big O, but then you also do want to look at real world efficiencies you can make. So you got to kind of keep both things in your head at the same time. But again, for the purposes of this example, I'm using this, non-efficient method without any of those improvements. So this method can be made more efficient from a real world perspective, although it will still be O of n squared. But for this purpose, I'm leaving it as it is, okay? Okay, so let's first of all run our code with a small set and make sure that it's, working properly. So again, here's our data set. Are there any duplicates in there? Nope. Let's run it again. Are there any duplicates in there? Nope. Let's run it again. Duplicates in there? Yes, 3 is in there twice. Okay, duplicates in there here. Yep, 0's in there twice. Okay, so code appears to be working just fine. All right, so let's now kind of increase the size. You can see again for small data set of size 10, it's, the running time is kind of the same for all of them. Let's increase to 100. Now we're starting to get a little bit of time there on the quadratic one. But it's still pretty it's still pretty low. And actually, before I continue to increase, let's go back down. We didn't actually walk through the theoretical for this method. So we talked a little bit about it, but we didn't walk through it. So again, the two main things you want to look at when evaluating the theoretical big O of your code are loops and method calls, and in particular method calls inside of loops. So let's take a look at this first loop here. This loop is dependent on the size of the list. Right? So this loop will run based on how big the list is. If your list is size 10, this loop's going to run 10 times. If your list is size 100, this loop's going to run 100 times. Okay? So that loop is dependent on n. Let's look at this loop here. Well, this loop is also dependent on n. For this loop here, again, if the list is 10, the loop's going to run 10 times. If the list is 100, the loop's going to run 100 times. But this is a nested loop. So the way that we account for nested loops is you take the number of times the inner loop is going to execute and you multiply it by the number of times the outer loop is going to execute. Because if you think about this, let's again say we have a list of size 10. For the first pass of the outer loop, the inner loop runs 10 times. So that's so far we've got 10 total, times through the code. For the second pass of the outer loop, the inner loop runs 10 times. So now we've got 20 passes through the code. For the third pass of the outer loop, inner loop executes 10 times. Now we've got 30. Fourth pass of the outer loop, inner loop runs 10 times. So now we've got 40 and so on. So by the time the outer loop has run its 10 times, the inner loop has actually execute 100 times, right? 10 times 10. So whatever code is in there that we're working with has actually executed n squared, 10 times 10 times. Okay, so that's what results in this method being n squared. Now, the other thing we want to be careful about is our method calls, but we know that get is O of 1. It's constant, so that's okay. Again, get is O of 1, so that's okay as well. So this whole method runs in quadratic time. Which is O of n squared. Now, again, what does that mean? It means that as the size of our data set increases, the running time increases. But the running time increases at a faster rate. So remember, a linear method, the running time does increase as our data set increases, but for a quadratic method, it also increases, but it increases faster. So for example, if we double the size of our data set, the running time might multiply by 4, by a factor of 4. Okay, if we were to multiply our data set by size 10, the running time might increase by a factor of 100. Okay, so the running time is going to increase at a faster rate. Okay, so this is, data times 2, and this is going to be data times 4. All right, so the time increase by 2 times 2, 2 squared, which is 4. Okay. So again, it's that nested loop that results in the quadratic running time. The n for the outer times the n for the inner. So the outer loop runs n times, but that's multiplied by that inner loop, which also runs n times, and that's where we get the n squared quadratic. Okay, so there's the theoretical evaluation of our code. So now let's go back up and look at the empirical timing. So again, we have a list size of 100, and we can see we got about 3 seconds. Okay, let's take it up to 1,000. Okay, we're at 38 seconds. So now let's start doing some doubling. So again, we're at 1,000 and we're at about 38 seconds, 33 seconds, 30 seconds, somewhere in that range. So let's double to 2,000. So we're doubling the size of our data set, and let's see what happens to our running time. 46, 29. So it's not really increasing that much, but this might be because we're still at pretty small data sets. So let's actually increase this to 10,000 and see what we get. Okay, so 10,000 here, we're at about 200 milliseconds. 184, 220, 208. So we're at about, let's say somewhere around 200 milliseconds. And as a reminder, our linear one took about 2. Okay, so let's now double this. So we're at 10,000. We're at around 200 milliseconds. Let's double it to 20,000. And here we go at around, 700, around, 660, 640. So again, it's multiplying by about a factor of 4, right? These aren't exact calculations, obviously, but the idea is to think about that rate of increase. Is it increasing at the same speed as your list size data set is increasing, or is it increasing faster? And if you look back up at our constant and linear ones, you'll be reminded that the constant time isn't increasing at all, and the linear one is increasing at the same rate. So again, we're around, 800 milliseconds. Let's double again. 40,000. Oh, you know what? I got to stop the printing out too. That's going to take way too long. So let's put it back to 20,000 for a sec here. So we're at, again, about, 800 or so milliseconds for the 20,000. Let's double to 40,000. So again, we've doubled the size of our data set, but now the running time, which was at about 800, is now at, 3,100. Again, it's increased by a factor of 4. Whereas you can look back at the linear and that's only doubled. So as we again double the size of our data set, our linear algorithm doubles in execution time, but our quadratic algorithm, the execution time is multiplied by a factor of 4. And if we double it again, it's now going to be, again, multiplied by a factor of 4. Okay, so that's the idea, is that you're not really looking at the amount of time that an algorithm takes to run. You're looking at how that amount of time increases as your data set increases. And here you can see that 3,000 was approximately multiplied by 4. Okay, and again, that's the key part. It's all about the rate of increase. So you're not comparing how long does this code take versus how long does that code take in terms of looking at the theoretical efficiency. You're comparing, if I double my data set, how does that affect the algorithm? This one or another one. Okay, so you're looking at that rate of increase. That's the really key thing to look at. Now, a couple other things I want to make note of here. Let's just put this back to 10 for a moment. One is that we've looked at nested loops, right? We looked at nested loops here in our contains duplicate, and both of these loops were dependent on n. And so that is what led to O of n squared code. If you have a nested loop that is not dependent on n, it won't affect the efficiency, the big O. So for example, if we go back to our linear time and we had a nested loop here, but let's say it's not dependent on the size of the list, it's just dependent on some constant. This is a silly example, obviously, but, we don't even have to do anything inside the loop. It doesn't matter, right? The idea is just that we are doing something 100 times, but this code here, this loop, is not dependent on n. It's constant time. Okay, so if the size of our data set doubles, for example, this inner loop is going to run 100 times. If the size of our data set is 100 and then increases to 1,000, this loop is still going to run 100 times. So adding a nested loop that is not dependent on n, but is just dependent on some constant, this method would still be linear. It does not change the big O of the whole code because this is not dependent on n. Again, we're always looking at the effect of how the code is going to change, the running time is going to change based on the size of our data set. Okay, so it doesn't matter if this is 100 or 1,000. That isn't dependent on the size of the list. So that's not going to change the overall efficiency of the code. Now, again, think about that real world running time, right? It certainly does matter if this middle loop is going to run 100 times or 1,000 times or 10,000 times. In terms of how long your program is actually going to take to run, yes, that matters. But that doesn't change the theoretical efficiency. The theoretical efficiency of this code here is O of n. And if it just runs 10 times, it's still O of n. Okay, so nested loops only matter if they're dependent on n, if they're dependent on the size of your data set. The other thing to be careful about is consecutive loops. So let's say if in addition to calculating the sum, we were calculating the product. So we had another loop here. And, let's say we're just printing those two values out instead of returning one, for example, this code would still be O of n because consecutive loops they're not nested together. So this code is, this whole piece of our code takes, on order of n to run. This whole piece of our code takes on order of n to run, but it's happening one after the other. It's not nested. So this would not be n squared. If we were thinking about the running time, this would kind of be like 2n. But in terms of big O, 2n is still order n. So consecutive loops, even loops that are, this part of the code is O of n and this part of the code is O of n, but they're consecutive. They're one after another. They're not nested. So this whole method is still going to be O of n. And again, of course, this method is going to take a lot longer with the two loops in here from a real world timing perspective, but the whole thing is still O of n. Okay, so again, theoretically, it's still O of n. It's still a linear method. Because as let's say our number size, as our list is size 10, we'll have 10 passes of this loop and 10 passes of this loop. That's 20 passes total. As we double to a list size 20, we have 20 passes of this loop and 20 passes of that loop. That's 40. That's, again, the whole problem size is double. If we double to 80, we have now 80 of this and 80 of this. That's 160. The whole problem size is doubled. So they're increasing at the same rate. We double the list, we double the running time. Okay, so again, you got to think about how that execution time changes as a result of your size of your data set changing. Okay, and things to be careful about are nested loops versus consecutive loops, and also loops that are not dependent on n. So if you have a loop that's dependent on some constant, that's not going to affect your big O. It, again, might affect in the real world how long your code takes to run, but it doesn't affect the big O. Two last points to make. One is to be careful about those method calls. So one other way that we could have written this contains duplicate method is we could have, instead of writing an inner nested loop, right? So this was one way to do it. The other way we could have done it was we could have written a call to the contains method. So I could have said, okay, if my number list contains, or I guess, well, it couldn't be contains, it would have to be index of. So, okay, so let's just say this isn't going to totally correctly figure out if it has duplicates, but it's just going to give you an example of another way that you could get n squared code. So if we were to say our number list contains the current number, now of course this is going to be true, right? Because we've just got the current number, but just stick with me for a moment and pretend that, pretend we had some method that was like contains, but it was, counting the frequency or something like that. Well, so this is a call to the contains method inside of a loop. But the important thing is, let's take a look at that contains method. If we look at the contains method, that is not listed as our constant time method, right? So if we go down to contains, we might be able to find more information about it here. We might not, but if you think about how a contains method works, right, it has to look through all of the elements in the list to figure out if that element's on the list. So the contains method is actually O of n. Okay, so here we're invoking contains from inside of the for loop. So this loop is dependent on n. This method call is dependent on n. So this would also result in O of n squared quadratic code. So if you have a method that runs in linear time, O of n time, and you put that method call inside of a loop, your whole algorithm then is n squared. It's quadratic. So that's something you have to really be careful about, is when you invoke these methods inside a loop, what's the running time of that method? If it's constant, like get, then you're probably okay. But if it's O of n, you've now created n squared code. And we in general want to avoid n squared code. All right, so let me take this out again because it doesn't obviously actually work to find the duplicates. But again, it's just an example of being careful of method calls inside of loops. One last final point here to note is that even bad, quote, bad code or inefficient code is probably okay with small data sets, right? So here, if our list size is 1,000, yeah, our quadratic code takes longer, but it doesn't take that long, right? And even if we multiply by, if we double to 20, to 2000 rather, yeah, our running time is increased, but it's still, again, pretty quick. So sometimes if you always have small data sets, it's not a big deal to have code that's n squared. But as you start getting into bigger and bigger data sets, it does matter. So if we have, 100,000 elements, it matters if we have a linear algorithm or a quadratic algorithm, right? And in today's day and age with data sets, 100,000 isn't even that big, right? If you think about, internet searches or things like that, 100,000 points of data is not a large number anymore. So a quadratic algorithm is going to be very problematic as you start getting into larger data sets. So you really want to be careful to evaluate that the theoretical running time, right? Is it O of n? Is it n log n? Is it log n? Is it n squared? And you want to get that as efficient as possible. But then, of course, you do also want to worry about that actual real world running time. Because let's say you have a linear algorithm, O of n. In the real world, if, a list of size 1,000, the loop runs 1,000 times, versus another code where there's 4 loops. So basically the loop has to run 4,000 times. Well, those are both O of n, but in the real world, one's going to take a whole lot longer than the other. So you got to, again, keep both of these things in mind. Okay? So hopefully this is a helpful kind of concrete example about running time, both empirically and theoretically. I encourage you to play around with this, add in some of those other loops that we've talked about, kind of change some of the loops, change some of the code and see how it affects things. Try to first evaluate logically, theoretically, how the running time will be affected, and then actually run it and do some tests and see if you can kind of see the behavior in real time. The other thing I encourage you to try is think about what would happen if this was a linked list instead of an array list. So in particular, look up what the efficiency is for the get method in the linked list class. It's not constant. So if you're invoking the get method on a linked list, it's going to change the overall big O of all these methods. So I encourage you to look that up, kind of, again, look at it first from a theoretical perspective. What is the efficiency going to be? And then actually run it and kind of see in real numbers and real time how using a linked list for that purpose is different from using an array list. Okay. So again, play around with this code. Hopefully this gives you a way to really get kind of a concrete example to see some of these big O efficiencies in action.